So now, this is not the exact circuit that we see here. It's very close. Instead of the light-dependent resistor, which we have here, whose resistance changes based on how much light is falling on it. When it is bright, it has less resistance. We'll hear a buzz like that. And then when it gets darker, there'll be clicks. So the clicks aren't terribly loud. Hopefully you can hear it. Let's bring it closer. Okay, so yeah, there's clicks. But in any case, I used this setup in the last video that I did. Not the exact last video, but the last full video. I made a short video after that. I'm going to pluck these other components because I just noticed this diagram right after I did the last circuit where we used the trim pot to set the timing, and obviously probably wouldn't use a trim pot. You'd have like some kind of sensor. So that's what the light dependent resistor is typically. So I kind of got to bend them like this because I got to put them in the same spot. I'm going to turn the power off while I do this to prevent a short circuit. I really don't have to worry because we got like 220 ohms of resistance minimum right there. So we just have a short when it goes to ground. You know, not a big deal because it's just a capacitor stored charge. But in any case, power is off, and there we go. So now the lamp is at the brightest setting right there. When I turn it on, we should have closer to the well, a quick rapid rattle, it looks like. So I thought it might go a little faster where we get a buzz. That was the word I was trying to think of, buzz. And I haven't had to edit this at all yet. And so there you can see it gets closer to a buzz when I get a light on it. Let's try the side light, see if that is well, this flashlight doesn't have a side light, never mind. Alright, so now you also see when I do the that's the steady light, that's a lower light. It's actually turning on and off rapidly, but there we go. Turn it on and off like that. So we'll turn the power off. One thing, this is a breadboard power supply right here. So I made a video covering the breadboard power supply. It is by far my most popular video. The vast majority, I don't know if it's most of the views I get a day, but it gets the most views by far. Just covering this component. So the other end of this plugs into the wall. It's got an AC to DC adapter, and it takes the AC from the house and then gives a steady voltage of 9 volts at the output here. And so you just plug that into a breadboard power supply. They come separately usually, and you can't buy them together if you really want to, but just be aware of that. Somebody got mad at me once because I just covered the breadboard power supply plug in it. I didn't mention that you know, it might not come with the adapter, but in any case, you need you kind of need an adapter. You could use like a 12 volt battery or something, but I had a power supply adapter, I should say. When I set it to 12 volts, it was actually giving me higher than 12 volts, and I was frying these things. I finally realized that was the problem. It wasn't giving them 12 volts. They're generally made for like 12 volts or less, and they output 5 volts. You just got these little jumpers there in the 5 volt spot. You can move it to the 3.3 volts. So that powers that rail, that powers that rail. There's also an offsetting right there. These top 2 pins over there are 5 volts on the left. The bottom pins on the left are 3.3 volts. And then this is completely separate. This is ground right there. So you don't plug one of these into those 2 spots. That'll be a short circuit. You would plug a jumper that has a female end in there and a wire that comes out, and wherever you want the 5 volts, like on the board, from that spot, or ground as well, you know, whichever one you want to do. This is an active buzzer. So we have a passive buzzer in this circuit. Again, I covered this in the previous video. The passive buzzer, it needs a changing voltage to click. So that's what we got. The capacitor, it keeps current from flowing through the passive buzzer too long. It clicks when the output goes high and clicks when the output goes low. We have the A stable, that's why it's just you know, pretty steady clicking right there. It's astable. It keeps changing high and low. Without a capacitor, current should just keep flowing through it. So hopefully won't damage it, but any case, that's what it does. This is an active buzzer. So we could have the 555 timer go slower, but as long as the output is high, I'll pop this out. We could see what it does if I connect it. Right there. Okay, nothing. It's going too fast, I guess, to get it to beep. That's interesting. Or maybe can't provide enough current. But yeah, this is going to be a loud screech. If I accidentally put it in the negative. That's a loud screech. I can kind of dampen it like that. But yeah, that's what the I'm looking through the camera. There, you know, I can muffle it pretty well. Give me a little struggle popping up. Now, if I plug this one directly to the board, we got like that click, you know, and I think it kind of rattled when, like, I made and break connections. But yeah, we got that right there. You don't keep a steady voltage on the passive one. You want to alternate it, and you can do that with the capacitor right there. So I'll turn this off so it's not so annoying. I don't know what the perfect value capacitor is. If it doesn't sound right, you could, and you're using a low value, you could try like a larger value or something, and vice versa. Try larger and smaller values until you know, you're getting a sound that you think you should get. So I don't make a lot of circuits like this. I don't make any professional circuits like this or anything. It's just a test circuit right there. So I just am using 10 microfarad capacitor because it's working okay. That capacitor over there is for the timing. So if you're new to 555 timers, they have timing. Now, it's not intended for like many minutes or anything. It's for a very small fraction of a second, or, you know, a few seconds. 10 seconds or something. I think even 20 seconds you're starting to kind of push it. But the I could be wrong, but anything like a minute or more, I don't think you're going to have reliable timing, and the capacitor might even have problems charging and discharging at that point. But we have the capacitor. It charges through resistance right there. It's going up to 2/3 supply voltage, which pin 6 senses. And then it starts discharging to 1/3 supply voltage, which pin 2 detects. Now, when the capacitor is charging, pin 7 is not doing anything. It's going through that resistance. So brighter light, less resistance, it goes faster. But sometimes pin 7 connects to ground, so we need a certain amount of resistance from the positive supply. Well, it's connected to ground. It's a direct connection, 5 volts across this 220 ohm resistor. And so that's about the minimum resistance I want when you got 5 volts directly across it. But in case, we got the charging mostly determined by how much light is on the light dependent resistor right here. I think some people might call it a photoresistor as well. But in case, if you get it dark enough, it's actually clicking more than I thought it would. I'll dim the lamp right there. You know, we can easily get it where it, you know, it'll probably click like sooner or later, but you know, hardly at all. So we'll turn the power off right there. So when there's less light on it, it's got more resistance. If you like really cover it and everything, it has hundreds of millions of ohms of resistance. I measured that before. And if you get a bright enough light on it, I think it'll get down to like maybe 5-10 ohms or something. So I never tested it out in the sun or anything, but you know, I got pretty bright light on it and got it to like tens of ohms, but it's not as bright as it could have gotten. So in any case, more light, less resistance, capacitor charges faster to 2/3 supply voltage. While it's charging, the output is high. So output is similar to what the capacitor is doing. It's getting that positive voltage, and the output is high. And then when it gets 2/3 supply voltage, pin 6 senses that, then pin 7 connects to ground. As I said before, any current going through the resistor goes right to ground right there. We'll have 5 volts across that resistor there. It doesn't have anything to do with the discharging of the capacitor, and the capacitor will discharge through the light dependent resistor. So it probably has at least a little bit, maybe a lot less resistance while it's discharging there, depending on whether it was a lot higher than 220 or a lot lower than 220. Be aware of that. So the output's not going to be a perfect square wave. 50% duty cycle is what I was trying to say, where it's high 50% of the time and a low 50% of the time. It's going to be thrown off, you know, in this case, depending on how much light is on the light dependent resistor. So discharges down to 1/3 supply voltage, or if it's lower even, then the opposite happens. The output will go high. So when it's discharging, capacitor's discharging, the output is low right there. I think I missed that step. And then when it gets down to 1/3 supply voltage, then it stops discharging through 7 there. And capacitor charges, and the output goes high. The capacitors, though, they let alternating current pass through them, but not direct current. So what that's ultimately saying is direct current charges the capacitor. Once it's charged, it stops current. If it's alternating fast enough, it never fully charges. So current can move in and then discharge. Charge, discharge, just really rapidly before it can like fully charge or discharge, if you go fast enough. In this case, it's probably charging until it's full and then discharging until it's completely discharged, and so on. But it doesn't matter, we just need short burst of current for the passive buzzer. Pin 4 is the reset pin right there, and we don't want to reset the 555 timer in this circuit. That would set the output low and hold it low. That's if you connect pin 4 basically to ground. It has to have a pretty good connection to ground. If you put it to like 2.5 volts, it's not going to reset. You have to get really close to 0 volts. So you pretty much want a direct connection to ground. Pretty close. And we're making it where it never resets. That's all it's going to do is hold the output low. We put it to the positive supply. It doesn't do anything then. It lets these other two inputs control the output. And I heard it's not all 555 timers, but if you have the NE555 or the Micro A555, then pin 2 should be more powerful than pin 6. So they're looking at the same voltage now, and they're looking at two opposite voltages. 2/3 or higher for 6, 1/3 or less for 2. They're never fighting with each other because it will never be above 2/3 at the same time as below 1/3 in this setup. I have that jumper connecting the two together. If we wired them separately, which I do in some of my circuits, pin 2 has one voltage it's looking at, pin 6 is another. Usually you got a pull up resistor for 2, so most of the time it's looking at 5 volts through a resistance. Pin 6 most of the time is looking at ground through a resistance, and then you can have a switch where 2 will then connect to ground, and a switch where 6 will then connect to the positive supply. If you press both those switches at the same time, remember they're not sharing the same jumper in those circuits. Press them at the same time, pin 2 is the more powerful pin. So 4 is the most powerful pin. It will overpower pin 2 right there, because 4 is going to hold the output low no matter what. Pin 2, if you give it a low input, it tries to pull the output high, but it won't. And then pin 6 puts it low, which 4 already does, so we don't have to worry about that. But if pin 2 is holding the output high, and then you try to get pin 6 to set the output low, it won't go low. Pin 2 is more powerful. There are some 555s though where the rules are the opposite, so I don't think I have any, but I've read of them. So in any case, again, we started off the trim pot. I had that in a previous circuit, and you know, I had to turn the trim pot to change the tone. Here we have the light, and I don't think my camera was picking up the sound terribly well in the previous video, so I'll get a little bit closer here. But yeah, there you can see flashing light. We have that noise right there. So this is a way you could get that noise if you really wanted that noise for some reason. Whenever I show a circuit, I mentioned this in the previous video, it's not that I think the circuit itself is all that great. When I build circuits, the majority of them are just for learning how the components work and stuff. And I try to come up with as many ways that I think will make an interesting demonstration circuit. You know, I don't try to make circuits where they're not doing anything at all as far as you can tell. You know, I try to make it where they're either making a noise, you see LEDs flashing or something. You know, usually you're not making circuits to flash LEDs, but when it comes to the output, I kept talking about when it's high or low in this video, and you know, there's really no visual way to see it. You can hear the clicks when it goes high or low, but you can't even tell which one's high or low unless you got really good ears or something. You can tell because you don't quite get the full 5 volts. It doesn't connect ground. Also, the timing usually isn't perfectly halfway. So, you know, maybe you can tell when it's high or low. But with LEDs, you really can, because I color code them so that the blue one lights up when the output's low and the red one lights up when the output's high. So, in any case, I, you know, rambled on probably longer than I should. I filmed this all in one shot, first try. So, I'm just going to keep going. By the way, didn't mention it, we got dual inline package. That's when you got pins on both sides of the integrated circuit. As you can see there, this is an op amp, and I showed it in the previous video. But yeah, pins on both sides. There's little divots there. You start at the top left, work your way down, however long it is. You know, maybe it goes down 7 pins. Then you jump across and then up to 14. Here we go down to 4, jump across, and then go up to 8. And then when you look at the data sheet, the pin numbers, you might have this set up too. It might show the pin numbers and the names, or might have a drawing like this where it shows the names and so on. Ground is negative supply. VCC is positive supply right there. Trigger is pin 2. As I said, it's waiting for a low input, so it's the trigger. Output is 3 right there. So you can see that's going to the capacitor. The schematic is not usually drawn the way that you see the component on the pin layout, I should say, right there. Usually it's drawn for a nice flow for seeing what the circuit does. Generally, positive works up, down towards negative, down, lower, and then often from the left to the right for positive and negative. In this case, it's more we got the input on the left, the output over on the right. Our little control circuitry. That's what this is. 555 timer. It's a bunch of control circuitry in a package. There's all kinds of circuits. You can look up the schematics. You know, they build it into, you know, just I don't know how to explain how they build it into there, but they basically have a way where they can make little components inside the integrated circuit without, you know, the components having packaging. They just have the electrical parts of them, the semiconductive parts, and they find ways to get them to pass current to each other inside of a package right there. So that's our control, though. We got our input to the left. Usually control is more in the middle, and then your load or whatever it's controlling off to the right when you look at schematics. And the NE555 and the Micro A555, you should be able to swap them out perfectly fine. They should work pretty much exactly the same. There's other 555s like the LM555, and I think it would work in the circuit. I'm not sure. It's not meant to really provide current, but not much current flows with this one. Just be aware of that, though, whenever you see the part number. Sometimes there's letters afterwards that just say it's kind of a modified version, or it might say P for plastic package if there's also metal packages or something like that. But usually letters in the front kind of gives you an indication of what kind of manufacturer they are, you know, acting like, and you know, might tell different ways that it's wired inside as well, which the LM555 is versus the NE555 or the Micro A555. It works a fair amount different. As I said before, also here pin 2 is more powerful. I didn't demonstrate this. Then 6 other ones, pin 6 is the more powerful input versus pin 2. Pin 4 should always be the most powerful, the reset pin. I never heard of any where you know, like maybe pin 2 would be the one fighting it. I haven't heard of any where pin 2 is stronger than pin 4. That doesn't make sense, but who knows? Maybe they made one for some reason. So, in any case, Went on a whole lot longer than I thought, but I hope you enjoy. Thanks for watching. Make sure you check out one of the other videos I'm posting on screen, and check out links down below. They all help a lot. I'll see you in the next video.